Hello. Today we'll be discussing a few problems related to electric current. We'll be discussing more of such problems in other videos as well. So the first type of problem gives me an expression for charge with respect to time, that is q of t is equal to 5t square plus 4t plus 6 in coulombs. Now we are supposed to calculate the current, that is the instantaneous current. Okay, so instantaneous current is to be obtained, and we obtain it at t is equal to, let's say, 5 seconds. Now in order to obtain this value, the instantaneous current, what exactly do you mean by the term instantaneous? Instantaneous current is what you measure in an ammeter. Okay, is the value that you obtain in an ammeter while calculating the current passing through a given circuit at a given instant of time. And it is at a particular instant, obviously. So here, as per the question, it is 5 seconds. Now I is equal to dq by dt, that is the value of instantaneous current, and d by dt, that is derivative with respect to time, and we differentiate it, and the value of q is taken from the expression that is given, that is 5t square plus 4t plus 6. Now if we differentiate that with respect to time, we have that to be equal to 5 goes outside, d by dt of t squared plus 4 goes outside, d by dt of t plus the derivative of constant, that is 6, is equal to 0. And this is equal to 5 dt squared divided by dt, that is equal to 2t plus 4, where dt by dt goes to 1, and obviously the last term is 0. So that is equal to 10t plus 4. Now this is the expression for current, and we need to obtain the value of current at time t is equal to 5 seconds. So we substitute the value of t with 5. So the value of current at t is equal to 5 seconds is, we take the 10 and multiplied it with 5 plus 4, that gives me 50 plus 4, that equates to 54 amperes. Now this is the answer that we are looking for. On the other way around, if we are given an expression for current with respect to time, that is current is varying with respect to time, suppose, and that is equal to, suppose given as 4t plus 5 in amperes, then let us calculate the amount of charge that flows through through a given conductor over an interval of time. Suppose t is equal to from 1 seconds to t is equal to, let's say, 3 seconds. Okay, now in order to calculate this value of charge, we take we integrate I over dt within the given limits, and the limits being from 1 to 3. Now we write down the expression for I, that is 4t plus 5 times of dt taken from 1 to 3, that is 1 seconds to 3 seconds. And just by following simple integral calculus, that is 4 goes outside, we have t dt integrated from 1 to 3 seconds, plus 5 is a constant, stays out, so only the integration of dt taken over the limits 1 to 3. So this is equal to 4 remains as such, t dt gives me t squared divided by 2, and it is taken from 1 to 3 seconds, plus 5 dt integrates to t taken from 1 to 3, and this is equal to, the 2 gets cancelled out with 4, so what remains is 2 over there. So 2 t squared 3 squared as per the upper limit minus the lower limit is 1 square, and 5 again in the brackets we have 3 minus 1, the upper minus the lower. That is equal to the charge that we were to calculate, that is equal to 2 times of 9 minus 1 plus 5 times of 2. So that equates to 2 times of 8, that is 16, plus 5 times of 2, that is 10. So this is 26, and that is in coulomb, because the question was in amperes and seconds for current and time respectively. So 26 coulomb is our required answer. Now we try another type of problem where we have suppose say we consider some electrons, and they are drifting along a given conductor, and they are drifting along the conductor which along a certain direction, suppose, and the number of electrons that have been given is suppose equal to 1.5 times of 10 to the power 18. Again, we have some positive ions, and these positive ions are obviously the number of ions is 10 to the power 18, and they are drifting in the direction opposite, right, in opposite direction to that of the electrons. Obviously a field will drive them in opposite directions. So these are the electrons and the ions drifting, and that is per second. So we have the applied voltage across the wire or conductor, that is equal to 240 volts. Then let us calculate the effective resistance of the circuit. Now, in order to calculate the effective resistance, first of all we need the current that is flowing, and in order to know the current we must know the amount of charge, the total positive charge that is moving across the conductor or flowing across the conductor per unit time, that is per second. Now the total positive charge is to be obtained from the data that has been given, that is 1.5 is the number of electrons and 1 is the number of positive ions multiplied with 10 to the power 18, of course, and this 1.5 is the number of electrons which is negatively charged particle, or negative charge, and negative charge flowing in opposite direction. Negative charge flowing in opposite direction is the same, or in the backward direction we can say, is the same as positive charge flowing in the forward direction. So we just add them up, that is 1.5 plus 1 times of 10 to the power 18, because both negative charge and positive charge are now considered as the positive charge flowing in the same direction. So this is the number of positive charge. Now this is the number of positive charge that is flowing per unit time, but obviously that is the number, that is not the current. The current hasn't been obtained yet. So the total charge that is flowing, that can be obtained, that is flowing per second, is nothing but the current. Okay, so the current I will be equal to the value that we have over there, that is 2.5, that is 1.5 plus 1, that is 2.5 times of 10 to the power 18, and that is the amount of positive. Okay, let me change that. That is the number of positive charge that is flowing, total number of positive charge, and so the total amount of charge is equal to 1.6 times of the total number of positive charge, 1.6 into 10 to the minus 19, which is the value of single unit of charge, coulomb per second, that is ampere, that is the current. So now we can calculate the effective resistance, that is equal to V by I, and V is 240 divided by I, that is 2.5 times of 1.6 into 10 to the power minus 1, which comes from 10 to the power 18 and 10 to the power minus 19 multiplied, and this results 1.6 can be converted to 16, and we can have the liberty of taking 10 to the power minus 2. So 8 goes 30 times in 240 and twice in 16. So twice of 2.5 is 5 in the denominator. 5 30 by 5 gives me 6, and 10 to the power minus 2 goes up to 10 to the power plus 2, and we have 600 ohms. In another type of problem, we just calculate the ratio of the resistance. So two wires, and the ratio of the lengths is given to be equal to 1:5. And now these wires, their diameters, that is of the ratio d1 is to d2. First wire with respect to the second wire is equal to 3:2. And we just need to calculate the the resistance of one of the wires. Now if the resistance of the first wire is given to be equal to 180 ohms, then we just find the resistance of the second wire, that is R2. Now the two wires, they are of the same material. Okay, considering them to be of the same material, their resistivities are the same, that is rho 1, the resistivity of the first wire is equal to rho 2. And so now we have the ratio of the resistances as R1 by R2 is equal to rho 1 L1 by A1 divided by rho 2 L2 by A2. Rho 1 and rho 2 are same, remember. Now 180 is for R1, that has been given previously, so rho 1 and rho 2 cancel out, and all we are left with is L1 by A1 times of A2 by L2. Now L1 by L2, the ratio is given, that is L1 by L2 times of A2 by A1, and that is equal to L1 by L2 is given over there, that is 1:5 multiplied with pi d2 d1 square by 4 in the denominator, pi d2 square by 4 in the numerator, for A1 and A2 respectively. So pi and 4 cancel out, that is equal to 1/5 times of d2 square d2 by d1 whole squared, and this is equal to 1/5 d2 by d1. d1 by d2 is 3:2, so that is just the reverse, that is 2:3 for d2 by d1 and whole squared, of course. So this is equal to 1/5 times of 4 by 9, and on the left hand side we have resistance R1 by R2. Now R1 is given, that is 180, so we need to find R2. So R2 will be equal to we just cross multiply them, that is 180 for R1 stays there, R2 goes to the other side, while from the other side we have 4 in the denominator cross multiplied, and 5 and 9 in the numerator. So 4 cancels with 180 as 45 times, so we have 45 times of 45, so we can calculate that, that is square of 45, 2025, I guess, that is the resistance. Now conversely, if R2 is equal to 180 ohms and we want to calculate R1, so the resistance of the second wire now is 180 ohms, and we just need to find the value of R1. So we have that ratio over there, we had obtained that, so we just put it like that, R1 by R2 is equal to we have those ratios, that is over here we had it as 1/5 times of we had, I guess, 9/4. No, I don't think it's 9/4. I think that'll change. Okay, that is yes, that is 4/9. You can check it for yourselves. So R1 is equal to R2 times, that is 180 times of 4 divided by 5 times of 9. 9 goes 20 times, and again 4 times with 5, so we have 16 ohms. So that is the value for R1. And then let's switch over to the next question. What is given over here is that we have a copper wire, and that copper wire has an area of, let's say, 10 to the power minus 7 meters squared area of cross section. And what else? We have the resistivity of no, it's not the resistivity, it's actually the density. We have the density of copper wire to be equal to 9 times of 10 to the power 3 kg per meter cube. And we have also been given that 63.5 grams of copper make 1 mole, and 1 mole, let us say it is 6 times of 10 to the power 23 number of atoms. It's actually 6.023, but as per the question that we have been given, it's 6 into 10 to the power 23. Now if each atom contributes 1 electron, so we have 1 electron per atom, then we can have 6 times of 10 to the power 23 number of electrons that can be contributed in a given conductor of copper of 63.5 grams. We need to calculate the drift speed or the drift velocity. If the applied current in the circuit is or the obtained current in the circuit is 1.5 ampere. Now I is equal to NEA times of the drift velocity, or we have the drift velocity to be equal to I divided by NE times of the area of cross section. So we just need to find N, because we know the area is given directly and we know the charge of the electron. So N is essentially the number of electrons and that is obtained, that is available per unit volume. So the number of electrons per meter cube, number of electrons per meter cube. That is simple thing to obtain if we consider the above values that have been given to us. Now in 1 meter cube, the mass of copper contained is 9 times of 10 to the power 3 kgs. Okay, now in 63.5 grams, that is 63.5 times of 10 to the power minus 3 kgs, we have 6 times of 10 to the power 23 number of electrons, number of atoms actually, and each atom is contributing 1 electron. So 1 kg will contain how many electrons, or will contribute how many electrons? So that is unitary method, that is 6 times of 10 to the power 23 divided by 63.5 times of 10 to the power minus 3. So 9,000 or 9 into 10 to the power 3 kgs will give how many electrons? So that is 6 into 10 to the power 23 divided by 63.5 into 10 to the power minus 3 times of 9 times of 10 to the power 3. That is what we have for our given value. So this is the number of electrons per meter cube. That is what we were supposed to obtain, right? So we now have the value of N, so we can just substitute over there and find the drift velocity. That is Vd is equal to I divided by NEA. You might just remember the value of the expression for N that we had just obtained. For I, we just substituted with 1.5 ampere divided by N. Now the value of N that we had obtained was of the form of 6 times of 10 to the power 23 divided by 63.5, which goes up 63.5 times of 10 to the power minus 3, and at the bottom we have 9 times of 10 to the power 3, and then we put the values of the charge of the electron, that is equal to 1.6 times of 10 to the power minus 19, and the area that is given over there, that is 10 to the power minus 7. Now if you check the powers of 10, the minus 26 and plus 26, they completely cancel out in the denominator, and if you see 1.6 would have gone 40 times had that been 64, but that is 63.5, so which is 6.4 less than 64. So roughly 1.6 goes approximately, it goes 36 times. I can use the word approximately over there, 36 times over there. Okay, so 36, 9 cancels with 36 to give 4, and 1.5 cancels with 6 to give another 4. 4 and 4 cancel out, so we are just left with 10 to the power minus 3 as the drift speed in meters per second. So this is how we calculate using the drift using problems related to drift velocity. Some more problems on drift velocity can be like this, like if it's given that we have an applied potential difference of 100 volts, and that is applied across a distance wire of length, suppose say 100 centimeters, which is equal to 1 meter, of course. Now from those datas, again we've been given the number of electrons, or the number of electrons essentially, per unit volume, that is equal to 2.9 times of 10 to the power 28 per meter cube, is the number of electrons that is flowing per unit volume. And we have been given the uh, conductivity of the material of the wire to be equal to 5.8 times of 10 to the power 7 ohm inverse meter inverse. Now suppose the question, as per the question, we are supposed to calculate the drift speed, and from drift speed, all the values that have been given, we can use NEAVD. Okay, that is VD on both the sides. That cannot be correct. Actually, we have the right hand side, we have current divided by NEA. That's the correct formula. So now the current, is it given? No. Area, not given. E, we know that, and N is given, so we have those values over there. I by A is nothing but current density, that is the current per unit area. And is that given? No, still not available. So we can just obtain that from sigma times of the electric field intensity. The J is equal to sigma E, we know that. But is the electric field given over there? So electric field is not available, but however we have voltage and length, so we can calculate it from that. So that is V by L gives me the electric field. So for drift velocity, we just need sigma times of voltage divided by NE times of the length. Sigma is given, that is 5.8 times of 10 to the power 7, voltage of 100 volts, divided by N, that is the number of electrons per unit volume, that is 2.9 times of 10 to the power 28, okay, multiplied with the charge of each electron, that is 1.6 times of 10 to the power minus 19, and the length obviously is 1 meter, so we just put 1 over there. So that is equal to 2.9 goes 2 times with 5.8, and the powers over there, they kind of cancel out, because 19 goes up, so plus 19, and this thing goes up, so that is minus 19, and that gets cancelled out. So all the powers, you can check for yourself, they cancel out actually. So we are left with 2 divided by 1.6, and 2 divided by 1.6 is 1 point, I think it's 25, 1.25, yes. So 1.25 is the drift speed in meters per second, considering the units given. That's all. Thank you.